last couple problems with 310 happened today. It's going to be word problems involving differentials. And just to give you a quick recap of differentials, we know if we have a derivative, like a function like y equals 3x squared, something like that, and we did 1 dy equals 6x dx, right? Those are differentials. You differentiate the object, but then you put d, whatever letter you're dealing with, next to that object. And dy and dx represent errors, all right? The amount of error in measurements, and x and y would represent the actual measurements if we're talking about specifically using this to establish error of things. So that's how we're going to be using differentials today. So when we look at a word problem involving differentials in this section, and you look for keywords like what is the maximum error, stuff like that, that means we're working with differentials. Okay, so that should let you know that it's a differential problem when you're reading the word problem. Okay, it tells us the radius of a sphere was measured and found to be 21 centimeters. So the radius measurement is 21 centimeters. I'm using r for radius because that's what we always use for radius. Okay, with a possible error in measurement of at most 0.05 centimeters. Okay, so the person reading the tape measure, that's the centimeter tape measure there, puts it down, and they know that that's right, but they could be off by as much as 0.05 centimeters. Okay, so it's probably scaled in such a way that it's kind of in between dashes, and each dash is 0.05 centimeters. So they can tell that the worst they're off by is 0.05 centimeters. That means that dr is equal to 0.05 centimeters. So whenever they tell you that there's some kind of an error happening, that's d whatever letter they're dealing with. All right, so whatever measurement you're dealing with there, that's how you handle that. All right. They want the maximum error in using this value of the radius to compute the volume of the sphere. So the concern we have is what's the volume area? What's the volume error? So volume equals something. The error in volume is equal to something. That's what we care about, is the error in the volume. Okay, so if dr is the error in the radius, then dv is the error in the volume. All right, so how do we find volume of a sphere? On that sheet that I gave you in freshman year and told you to memorize before your senior year. 4/3 pi r cubed. Very good. 4/3 pi r cubed. All right. If you haven't memorized it yet, you still have time, but memorize it. It's just one of those things. When you go to take the ACT and you know that sheet like the back of your hand, it's so much easier to take the ACT. So memorize that sheet. Know all the formulas well. All right. Volume equals 4/3 pi r cubed. That's the volume formula for a sphere, and I know the radius, I know the dr, where there's no dr in this formula right now, right? All right, but if I differentiate, making differentials, I'll get some drs and dv's showing up, all right? I don't know what v equals, but just like with the related rates problems, when I differentiate this, what's going to happen to v? But if I differentiate v, it's going to change to 1 dv. V goes away, right? So I don't even need to know volume. Sometimes you do, sometimes you don't. All right, so again, it's dependent upon the equation you're dealing with. So we're trying to find an error in volume, a volume formula relating volume and radius, which is what we're dealing with here, is right there. Differentiating volume gets me 1 dv. V goes away, so I don't need to know what the volume is. If I did, I would just simply have to put 21 here. So if you do actually want to know what v equals, you're going to use the actual radius to find the actual volume. All right, the error doesn't matter in that sense. All right? So 1 dv is equal to, and then if I do 3 times 4/3 pi, that's going to be 4 pi r squared. And again, I'm going to harp on this until you guys quit making mistakes. I do not have to use the product rule there. All right? 4/3 is a number, pi is a number, r is a letter. I've got a number being multiplied by a letter to a power, so it's simply power times number, and drop the power by 1. There's a simple power rule going on there. There's not a product rule necessary. Then I'm going to put a dr next to that because, again, there is an r in that expression, taking differentials. All right? Some of you using the product rule when you don't need to, making calculus so much harder than it has to be. Calculus is hard by itself, so make it as easy as you possibly can. All right, next. What I want to find out is maximum error. I know what r equals. I know what dr equals. I have an expression here that has to be evaluated. So dv, what I'm looking for, is going to equal 4 times pi, use the pi button, not 3.14, we're not in algebra, 4 pi times r squared. 21 squared is 441. And dr is 0.05. And then if we just type that in our calculator, I forgot to have that open. Typed in this one, 4 pi times 441 times 0.05. We end up with 277.08847. I'm going to go 0.09 cubic centimeters. This is a change, an error in volume, so we're going to go cubic centimeters. And that might seem like a bad thing, right? Like, wow, we're off by that much. That seems like ridiculous. Okay, let's go back to the volume formula here. Let's just figure out what V equals just because we can. Okay, if I go again with this radius into this formula, again, ignoring any errors, because again, we want to always compare our error to our actual volume, which would be based on the radius we have. If I type in, I'll do it on the computer here, 4/3 pi r cubed, so it's going to be 4 times pi times 21 to the 3rd power divided by 3. Comes out to 38,792.39. 38,792. 0.39 was it?
Yeah.
Okay, that's the volume of the sphere based on this radius. Based on this error, we're at most off by 277.09. All right. Now, if we want to know how bad of an error something is, it doesn't have to do with the size of the number itself. It has to do with the size of the number compared to the actual measured volume. All right. So anytime they want to know, is this a decent error, all we're going to do is we're going to figure out the percent error. Okay, this didn't ask for it, but sometimes they do ask for it. I want to make sure you know how to do this. So, if I take the actual error we figured out, 277.09, divided by the exact volume given the radius they measured, 38,792.39, and I multiply that times 100 to make it a percent. All right, so error divided by actual volume is a decimal times 100 makes it a percent equals, that gives me a 7.14% error. Oh, hold on. I was going to say that's high. I left a 2 off of there. Let's try again. 277.09 divided by 38,792.39 times 100. Okay, so again, wrong number, right number equals. So it's a 0.71% error. Alright, that's pretty good. Alright, what's the volume of this? I've got it within a percentage point. I'm 99% accurate, actually 99.29% accurate there. That's pretty good. Alright, but even a little tiny discrepancy, that's not a very big error in radius, right? It still creates a massive error in volume because, again, volume is related to 3 dimensions. You mess up one dimension by a little bit, it messes up the overall volume by a lot. But again, by percentage compared to the actual volume, it's not that big of a mistake. Typically, you know, depending on what you're building, they have rules for the air has to be within this threshold. That would probably be outside the threshold, actually. 0.71. There we go. All right. So you probably want to be actually a little bit more accurate than that if you're measuring something that's going to be bearing weight or maybe driving cars over a bridge or you're building a building of some sort. You probably want the error to be closer to that, have better measurement systems than what they have.